Our first topic in calculus is limits. The limit of something, like the limit of this car is hopefully me, and it won't hit me, and it will never reach me. That is a limit. So if we were to graph this path of this car here with the time and the position, it might look something like this. And then it started moving away from me, right? So its distance from me looks something like that. And it was at about 15 seconds, I think. At about 15 seconds there, I was fretting for my life, right? So we say this: the limit as the time was going to 15 seconds, function f of x, we'll call it the forerunner there, is 1 if this y value is 1. All right, so that is, in this case, the lowest y value that this little graph gets. So anyways, well, that is a limit. So a limit of a function is defined like this: if f of x becomes arbitrarily close or really close to a single number L as it approaches some c value from either side, then we say that the limit of f of x as x approaches c is L. All right, so we're missing something here. We write it like this: the limit as x goes to c of f of x is L. All right, so we have two types of limits. We can talk about left-hand limits. That's limits coming from the left side. And we write that like this with a little negative sign. And right-hand limits as x comes to some value from the right side. And then we can have a limit, just an overall limit, if they're both the same. All right, so if we take a look at this here we got a couple functions, and let's look at their limits. So we want to look at this limit here of this function f of x. We'll look at this guy right here, x minus 1 over the square root of x minus 1. And we want to find out what happens as x is getting close to 1. This is positive 1 from the left side. What's going on as it gets close to positive 1 from the left side? So, all right, I got to take this point here and come over here from the left side. What's happening now? We're watching x. We're watching this x value here. As x gets close to 1, what's happening to this y? All right, well, let's get that point going again there. Okay, so it's getting close, 0.8, 0.9, so on and so forth, getting really close, really close. That looks like it's getting close to 2. Okay, but it just kind of disappeared there. What is going on there, all right? So something happened. All right, well, it was getting close to 2. Now we want to find out what's happening as we come from the right. So as we come from the right here, and as this x value gets close to 1, what's happening to the y value? Well, that y value is getting close to 2. But what happens at that point? Well, at that point, it's undefined. All right, so when x is 1 is undefined, all right? So, but it's getting close to 2 from both sides. So we say that the limit from the left side is 2. The limit from the right side was 2. They were both going to 2. So the overall limit as x gets closer to 1 is 2. Well, how about if we switch this up here and we've got x minus 1 over x squared minus 1, all right, instead of that square root. Let's change that square root to a square. Now notice that when x is 1, we got a problem here because the bottom's 0 and the top's 0. So 1 is undefined when x is 1. So we just want to see what happens when we get real close to 1 again, all right? So here we are. Here's our graph. And we'll bring this over, all right? So here's our point. And we want to know as it gets close to 1, what's going on? Well, as we approach from the left, and as we get close to 1, this y value is, what does it look like there? Can you see that? It's about 0.5. So from the left, the y value is getting smaller, 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 and going to 0.5. As we come from the right, the y value, the height, is going to 0.5. So it's going to 0.5 from both directions, and when it actually hits there, then we'll find out that that point is undefined, as we know. All right, so we have a left-hand limit and a right-hand limit, and we have a overall limit of 0.5. So since these are the same, since we have the same left-hand limit and the same right-hand limit, we can have that. Okay. Now those last couple graphs had holes in them. We couldn't see them on Desmos there because the holes were so tiny. Okay, but that's what we call a removable discontinuity. And hopefully this sounds a little familiar from past math classes. But when we have a hole in a graph, that's a removable. Sometimes we'll have a point up here. Sometimes that point won't be there. But there's a break in the graph. And so that's called a removable discontinuity. Okay? A discontinuity is just a break in the function. It is not continuous. We can have discontinuities that are what we call a jump discontinuity. So here, the function's cruising along, and then it jumps. And it's cruising along, and it jumps. So there's no limit here as x goes to 1 in this case. So as x goes to 1, here the height is 0. Here the height is 1. So here the limit is approaching 1. Here the limit is approaching 0. Those are not the same. So we say that the limit as x approaches 1 does not exist. Okay, so right in this area, there it does not exist, all right? Here, the limit does exist. Coming from the left, we're going to a height of 1. Coming from the right, we're going to a height of 1. So the limit, as it says here, is 1. That limit does exist. Here we have what we call an infinite discontinuity, because as we approach from the left, as we approach 0 from the left, that is, it's going way down here. It's going down, 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 down. As we approach from the right, it's going up forever. We know this is an asymptote. And so these 2 points here are going to get farther and farther apart. They're definitely not the same, so this limit does not exist. They are infinitely far apart, so we call that an infinite discontinuity. So these discontinuities are breaks in the graph. So consider this function. We've got a piecewise function. Remember how to graph that? We've got the graph y equals x plus 1. That looks like this. And we've got the graph y equals x minus 1. Now, first of all, before I go too far, this is only for x's that are greater than 0. So that's the right side of the axis there. X minus 1 is a graph that has a y-intercept of -1, slope of 1, but it's going to stop there because this is only for points that x is less than 0. All right, so the question is, graph them and find the limit if you can. What's the limit as x goes to 0? So the limit as x goes to 0, well here, this line is cruising along expecting to be -1 when it hits the x-axis, or x equals 0. This one's expecting to be 1. So those are different. So this one does not exist. We can sometimes say D and E does not exist. Well, what about the graph of 1 over x cubed? This graph looks like this here. So what's happening? Basically looks like a pretty normal hyperbola. X cubed is going to change the shape a little bit. But the question is, does that limit exist? No, it doesn't exist. Does not exist there. That is an infinite discontinuity. Okay. Then we can have this case here where we have the sine of 1 over x. Let's look at that. Now this one's an interesting one because look what happens here. As we get close to 0, if we zoom in, let's zoom in and let's see if we can spread this out a little bit. What's going on? If you take a point and we cruise, watch what happens. That point bounces up and down and up and down and up and down, as that x value is trying to get to 0. So as the x value goes to 0 here of this point, the y value is saying, oh, okay, I'm going to positive 1. No, I'm going to negative 1. No, I'm going to positive 1. Negative 1. No, no. It just can't make up its mind. So this is an oscillating function. And so when we have this oscillating function, we have to say that the limit doesn't exist. And you can think of it like it just doesn't make up its mind. So this function is sine of 1 over x. Again, it's going to look something like this, and it starts to go back. Let's see if I can do a better job than that. Okay. It's going to go from 1 to negative 1 to negative 1. It's going to bounce around like that, and then it's going to come out like this. Okay? So the moral of the story is it's bouncing back and forth, so this limit does not exist. So those are those situations. All right, a couple quick limits here, and we can kind of see how we can get them from the graph. Let's check this out. We've got the limit as x goes to 0 from the left. So here we've got a piecewise graph, a whole bunch of different pieces. Kind of a complex looking thing, but we're just going to look at one part at a time. So look at 0. Well, what's happening from the left? Coming from the left, we're approaching 1, the height of 1. Coming from the right, we're approaching a height of 1. And that point is actually there, so that point actually is 1. The y value is 1. So the limit from the left is 1. The limit from the right is 1. And the actual value is 1. So f of 0 is the height of that actual point. How about at 2? What's happening at 2? Well, let's go look at 2. As we approach from the left, as x is getting close to 2, we're looking for an x value of 2. So we're going on this roller coaster towards an x value of 2. The height is going to 3. Okay, so the limit from the left side is 3. Well, what's happening from the right side? The limit from the right side, coming down the roller coaster, the height is 4. So that height is 4. And what is the actual value of f of 2? Well, is it 4? No, there's a hole there. Is it 3? No, there's a hole there. F of 2 is 2. There's the point right there. All right? So f of 2 is 2. So none of these match here. Okay? So we would say this, the limit as x goes to 2 doesn't exist for f of x. Okay, you should put f of x in there. Here, the limit as x goes to 2 of f of x is 1, because they all agree. How about going to 4? What's going on with 4? So we're coming to 4 from the left. So as we come from the left, it's going up to infinity. As we're coming from the right, it's going down to infinity. Okay? So really that limit doesn't exist, but we will say it kind of gives us an idea. It's going up to positive infinity. Infinity is not a number. So this really doesn't exist, but it's a special kind of doesn't exist. It's an infinite doesn't exist. Okay, so from the right side, we go negative infinity. From the left side, positive infinity. Those are going to different places. So the value of f of 4, well, the value of f of 4 doesn't exist because it's an asymptote. The limit doesn't exist, and the value doesn't exist. What about 6 from the right and the left? Okay, well, 6 from the left, we're going to 2. It's at a height of 2. From the right, we're at a height of 4. As x goes to 6, we're going to 2 from one way, 4 from the other. All right, so 2 and 4. 2 from the left, 4 from the right. And what is the actual value of f of 6? Well, where's the point? There it is right there. So the point is, the value is 4, okay? The solid point. So since that doesn't agree, we don't have an overall limit there either. And last but not least, what about at -2? Well, we got to be a little careful. This is going up to infinity. This is going up to infinity. However, again, infinity is not a number, all right? So they're not going to a discrete number or a finite number. So we're going to say does not exist. Okay, sometimes we will see, this is kind of a tricky one, sometimes we will say, you'll see that this limits be infinity, all right? So by saying that the limit is infinity doesn't really mean that the limit exists, because infinity is not a number, but it gives us an idea of the direction. So, all right, well, there's limits. That's the idea of it, all right? And there is a formal way to define a limit. It's called the epsilon delta definition of a limit. And if you are a math major in college, you'll use that all the time. But we'll leave it at that, and this is enough to get us by. So hopefully we got a good understanding there. So keep working hard and don't limit out. I want to look into